Okay, so today's project is an analog computer. And the idea for this came from the book I'm showing here, the Build It Yourself Science Laboratory. The original version of this book came out, I think, in the 1960s. It's been updated recently, and it's available on Amazon either in paper or Kindle form. I bought the Kindle version of it. My good friend Henry reminded me about this book, and it's a terrific book. It's got hundreds of experiments, great fun, just lots of hours of great fun in this book. So, what is an analog computer? Well, it's a computer where physical quantities such as voltages are used to represent numbers, and these physical quantities rise and fall smoothly. And just as math can be used to analyze a circuit, well, a circuit can be used to do math, and that's what an analog computer is. And it's pretty cool because it fosters an understanding of the problem that you're trying to solve and the analog circuit that models that problem space and the math that describes how the circuit works and how the problem works. And so it forces an integration of all those pieces together and merges the precision of math with the craftsmanship of circuit design. Back in the 1960s, there were a number of analog computers that you could buy for hobbyists. And so Edmund Scientific made one that's shown here in the upper left. Radio Shack made one that was similar. And General Electric made one that's shown here on the right. And so these were available out there to build a computer. The December 1961 issue of Popular Electronics had a whole article about analog computers. The link's here, and I'll put it in the description of the video. But this is 5 or 6 pages, I think, that describes how analog computers work. In addition to the hobbyist level computers, there were more capable ones that were used in military and industrial and academic applications. Here's a couple examples of them here. And an analog computer was used by the Marshall Space Flight Center in 1966 to do simulations of the Saturn V rocket that took us to the moon. Today, you can buy an analog computer shown here. It's called the Analog Thing, and you can buy it for about 500 euros. The one that I built, and the one which is similar to the one from Edmund Scientific and Radio Shack and GE, operate on the idea of voltage dividers. And a voltage divider in its simplest form is just 2 resistors in series, like this. And if you tap the voltage, or tap the circuit and read the voltage between the 2 resistors, the output voltage is different than the input voltage by the ratio of the resistors. A potentiometer is the exact same idea, except instead of having 2 resistors, there's 1 resistor with a wiper that can move back and forth across the windings. And depending on where you position the wiper, you can get a variable output voltage. So the way the computer works is there are 3 potentiometers, one here, and one here. And the way it works is the output from the first potentiometer goes to the input of the second potentiometer, and that creates a multiplication effect. And then the third potentiometer is used to balance the output from the second potentiometer. So here's the wiring schematic here on the right. So a potentiometer has 3 terminals on it. Terminal 1 is shown here, and so on potentiometer 1, terminal 1, that's connected to 3 volts. Terminal 3 is connected to ground. In fact, all 3 of them, terminal 3 is connected to ground. And then the output from potentiometer 1 goes to the input of potentiometer 2. And then the output from potentiometer 2 goes to one side of a galvanometer. The output from potentiometer 2 goes to the other side of the galvanometer, and then potentiometer 3 is adjusted so that no current flows through the galvanometer. Now, in my version of it, I didn't use a galvanometer. I used an analog ammeter. But what you need to do is measure the current here. And as long as the current is 0, you get the same effect, whether you use a galvanometer or an ammeter. So I created a Fusion 360 model of this thing. So I needed something to hold all this stuff together. So I modeled this holder here, and I 3D printed it. So here's the holder for everything. I modeled the potentiometers. I modeled a battery holder. So the circuit has 2 AA batteries, and the holder has a switch. There's a couple of jacks here that the multimeter is plugged into to measure the current. And then I printed some knobs that go on the shaft of the potentiometers. And one of my friends laser cut some acrylic, some transparent acrylic cursors to indicate the values on the scales here. So here's what it ended up looking like. So here's the printed 3D case and the knobs and the cursors. I printed dials that have 3 scales, one that's linear, one that's a sine scale, and one that's a log scale. And then here's a early 1970s Radio Shack multimeter that my father gave to me about 55 years ago. And this multimeter works as well today as it did in 1970. So this is a pretty cool setup. And here's what the internal wiring looks like. So I've got a 50 ohm potentiometer here and here. There's a 1K pot here. Here's the battery holder. Here's the banana jacks that the meter plugs into. And everything is all soldered together. Here's a close-up of one of the scales that I used. So this one has 4 scales on it. You can see there's a linear ring here that goes from 0 to 10. There's a sine scale here that goes from 0 to 90 degrees. There's a logarithmic scale that goes from 1 to 10. And then there's a tangent scale that goes from 0 to 45 degrees. So let's talk about how you would use this thing. So if you want to multiply 2 numbers, here's how you do it. Let's do an example multiplying 5 times 7. So we know that equals 35. So what you do is you set 5 on the linear scale of scale A, right? Here's 5. And you set 7 on the linear scale of scale B. There's 7. And then you adjust the dial on scale C so that the ammeter reads 0 amps and the cursor points to the answer, which in this case is 35. And here's a picture of it down here. So here's 5, here's 7, and here's 35. And then you can see on the ammeter here the amp scale is this black scale right here, and here's the pointer on it, and it's indicating 0 amp. 0 is on the far left side of the scale. If you want to square a number, it's a little more involved, but it does it. So 4 squared, you can calculate that by saying 2 times the log of 4. So if you want to do a squaring operation, what you do is you set the exponent, in this case 2, on the linear scale of scale A, and then you set the number to be squared, in this case 4, on the log scale of scale B. All right, so here's 4 on the log scale, and notice that it points to a number that's approximately 0.6. Well, the log of 4 is 0.602. So you can see here's 4 on the log scale, and here's a number just a little bit bigger than 0.6 on the linear scale. Okay, so in effect what you're doing is you're multiplying 2 times 0.6, but you don't have to look up the log. The log scale does that for you. So you just put the cursor on 4 on the log scale. So you know that the answer, that 2 times 0.6 is 1.2. So what you do is you turn the knob on scale C so that you get 0 reading on the ammeter, and what you'll see is the answer is 1.2. Well, 4 squared isn't 1.2, so you got to do a little more math. So the value of 1.2 has 2 parts. The characteristic is the number to the left of the decimal point, and the mantissa is the number to the right of the decimal point. So in this case, the characteristic is 1, and what that means is the answer is between 10 and 100. The mantissa is 2, and that tells you exactly what the number is between 10 and 100. So now what you do is you take that 2 and put it on the linear scale, and you read back to the log scale, and that indicates 16, which is the answer, right? So 4 squared, or 4 times 4, is 16. So here's what the analog computer looks like now, and it's great, but I want to add some more capabilities to it. So the first thing I'm going to do is I'm going to add more potentiometers to do cascading calculations. So let's say you've got a formula that involves a number of multiplication steps. The way I'll design it is so that the first multiplication, that product, will be the input to another computer just like this, and that will perform a second multiplication, and I'll do a few of them so that I can do a series of multiplications. And the way I'll do that is, instead of hardwiring everything and soldering it like I did in this one, I will use patch cables similar to the highly capable ones that I showed a couple minutes ago for the academic and industrial and military applications of this. I'll put in I'll use patch cables with banana plugs to connect them together, and then I'm also going to add op amps to be able to do addition and subtraction and calculus integration. And then my friend that made these laser cut cursors for me, he's also going to take this paper scale thing here, and he's going to create a version of that he's going to cut it out of acrylic with his laser cutters, and he can put the tick marks and numbers on here, so I'll have a little bit nicer scale to use. Okay, so there's more to come on this. It's going to take me a while to figure out how to do all this, but I know I can do it. I just got to design a bunch of things. I got to buy some more potentiometers and print a bunch of things, and I haven't done much with op amps, so I got to get smarter on how those work and how op amps can be used to do addition, subtraction, and integration. And the integration thing is pretty cool. What you do is you can put a capacitor on the feedback loop of the op amp, and then that can do integration for you. All right, so there's more to come on this, but this is a kind of a fun project. Okay, so now I'm going to do a demonstration, a live demonstration of my analog computer. Okay, so here's a demo on how the analog computer works. So let's do an example of multiplying 6 times 4. Okay, so let's zoom in here, and the first thing I'm going to do is I'm going to turn the knob on dial A to 4. Okay, like that. All right, and I'll zoom in a little bit so you can see it. See how the cursor's lined up with 4? Okay. Now I'm going to come over here to dial B, and I'm going to turn that one so that the cursor is indicating 6. See that? Turn it a little bit more, get it lined up. All right, so there's 4 times 6. And if you come up here to the multimeter, you can see on the DC amp scale here, the black ring, that's indicating that the current is falling. Okay, so now what I'm going to do is I'm going to turn dial C, this one, until the ammeter indicates 0 current. So as I turn the knob, see how the needle goes down? And if you get right on top of it here, I'm going to turn it down until I get 0 milliamps through the ammeter. And then you come over here to dial C, and if you zoom in a little bit, you can see that the cursor is indicating exactly 24. Okay, so that's how this thing works. Okay, analog computer.